Like many developers, I love working on code performance, getting deep into a problem, measuring, profiling, tweaking, squeezing out every last drop of juice from my code. I'm a Rails backend developer. I don't get to do that very often. Last year, I worked on this project where performance was key. And working on that project, I learned some interesting lessons. This is a talk about assumptions. First of all, though, hi, my name is Daniel, and I work for GoCarless. We are a payments company based in London, UK. As you probably noticed, I'm not originally from London. I come from Argentina. So in case you were wondering, that's the accent. Now, before I get into the interesting part of this talk, I need to give you a little background on the problem we were trying to solve. GoCarless is a bank-to-bank payments company, which basically means we're sort of an API on top of the banking system. When you're a payments company, your customers expect you to always be available, just like they expect the electricity to always work. So for us, uptime is critical. And that means, among other things, that having good metrics for our apps is critical. And this is where our project came in. One of the main tools we use for this is a metrics server called Prometheus. Now, we love Prometheus, but we have a pretty big issue trying to use it with Ruby. Prometheus basically keeps a history of what all of your metrics have looked like over time. And to get those numbers, it will periodically hit your app asking for them. So in order to have metrics, you're going to have your web server that's running your app. And in addition, it's keeping a bunch of counters in it. Say how many HTTP requests it served, how long they took, how many payments you took in different currencies. Prometheus will hit your app every few seconds, asking for those numbers, and you reply with something that looks a little bit like this. Now, Prometheus also has libraries that help you do this. These libraries allow you to declare your counters and set their values, and then when you get scraped, it automatically generates this output. And there's one for all major server languages. There's one for Ruby, sorry, there's one for Go, one for Java, and of course there's one for Ruby. And for most languages, the story ends there. However, in Ruby land, and by the way, also in Python land, the story is a little bit trickier, because Ruby and Python have a global interpreter lock, or GIL, which doesn't let you run your code in multiple threads at the same time. Because of this, our web servers tend to not be multi-threaded, because that doesn't scale very well. Instead, in Ruby, we tend to use separate processes. Processes don't share memory, and this ends up solving the same problem that the GIL is trying to solve, and everyone can happily run in parallel, ignoring each other. In the web world, we call this a pre-fork server, and it's how Unicorn works. When Unicorn starts, it will load your app, and then it forks itself into a master orchestrator process that's listening to requests, and a bunch of workers that are actually working on them. When a request comes in, the master process will pick a client to work on it, and then take the response and send it back to the client. The system works great. It scales really well across cores, and it's how the majority of Ruby web apps are running in production. However, for the Prometheus use case, this is a bit of a problem. Because now that we have multiple processes and they don't share memory, which was the whole point, each process now has their own internal counters. When Prometheus hits you and asks for all of your numbers, the worker that works on that process, on that request, will basically report its numbers. But this is never what you want, because this is a partial view of the system. What you want is the view of everything added together. However, because the processes don't share memory, there's no easy way for any process to see the numbers in the other processes to be able to add them, which is by design, and it's the main reason we use multiple processes. We want that isolation. But for the Prometheus use case, this is a problem. So since the majority of Ruby web applications are running in pre-fork servers, and since the Prometheus library doesn't have a solution for that cross-process aggregation, basically everyone that's using Ruby in production and wants metrics with Prometheus can have them. And we also had this problem. We were using Prometheus. We wanted metrics for our main monolith, which is Ruby, and we couldn't. And it wasn't just us. This has been the case for quite a lot of people for quite a while. And also, this Ruby library had a bunch of other problems. It was one of the first libraries to be made, so it was made before the community had figured out what the best practices were for these counters, and so it had a bunch of other stuff, other problems. Now, there were some workarounds. Most notably, GitLab forked this official library, and they had a multi-process solution, but it wasn't getting merged back into the main repo, and it also shared all of these issues with best practices. So we didn't want to use that, and we didn't want to make yet another fork. So instead, we got in touch with the maintainers, roughly agreed on a plan of action, and we decided we would do pretty much a rewrite solving all of these issues. But there was one more thing to consider. The Prometheus maintainers really care about performance for these libraries. Because instrumentation should be free for your app. If you're going to have your counters and you want to increment one of those in a tight loop, you should be able to do that and not even notice it. And buried in that long thread from that 2015 ticket, we had a target. Now, I've changed names to protect the innocent, but one of the main maintainers basically said that incrementing a counter should take less than a microsecond. Why a microsecond? I don't know, but that was his target. And if I wanted to get this thing merged, we were going to have to get there. Now, another maintainer of this gem basically went like, yeah, you're not going to be able to do that in Ruby. To which the first guy very reasonably responds like, I mean, surely Ruby can't be that slow, which leads to one of my favorite answers ever. I guess there's a reason people like writing C extensions, right? So whatever we did to solve this problem, it had to be fast. We had an actual target. And there was one more thing that the maintainers and us all agreed that we wanted to do. In the library, we have these metrics classes, which is what you use to declare your counters, and they store the value in an instance variable like this. We wanted to change this so that these numbers would actually be stored somewhere else, somewhere separate. We wanted to have stores that would be interchangeable and keep all of the numbers there. So we go from something like this to something a bit more like that. And the reason for that is that different projects would have different needs. Some people will be running in a single thread, a single process, and really care about performance, whereas some other people would have a web app in multiple processes, and they're hitting a database over the network, so who cares about microseconds at that point? Having these interchangeable stores gave our users better options, but also it made our lives much easier, because the hard bit about this problem was, the project was sharing these numbers across processes, right? Having these interchangeable stores meant it was very easy to just make a little experiment, put it up there and measure it, and we wouldn't have to touch anything else in the rest of the code, which was a really good pattern for experimentation. So to recap, we knew what we had to do. We were going to rewrite this gem so that it would support prefix servers, it would have abstracted storage of numbers, it would follow all of the current best practices, and it was going to be fast. And this is where we were at. We now needed to figure out how we were going to do this in a way that actually allowed us to share those numbers, but staying under that performance budget. Now, to store our numbers, we use hashes instead of integers, for reasons that will make more sense later. But for now, what this means is that when I say increment a counter, what I'm talking about in practice is reading and writing a value in a hash. And according to this exchange, this either could or couldn't be done in a microsecond. Now, I don't know about you, but if you had asked me whether this was possible before this project, my answer would have pretty much been a meh, because I have no intuition of Ruby performance at this level. Here, one guy is implying that Ruby is very slow. The other one is saying, like, surely writing to a hash is faster than that. But this is such a tiny scale compared to my usual experience that I have no idea which one is right. What I mean by that is my entire Ruby experience for the last decade is writing the backend of a web app, right? So I'm used to a world of performance that looks a little bit like this. Let's imagine that that's a second. That's 1,000 squares, 1 millisecond each. As a web programmer, this is how I see the world. There's nothing smaller than a millisecond for me, right? So I'm running my web app, and a request comes in, and there's a couple of milliseconds taken by Unicorn, Rack, Rails, I don't even know, but before it even hits my code, I lost those two. There's a user ID in session, so we're going to hit a database to load that user. It's a well-indexed table, so it takes just a millisecond. The page we're loading is actually a list of the orders for this user. So we're going to hit the database to load those orders, and we're going to hit it again to load the items for those orders. Then we're going to hit it a bunch more because we had an n+1 that we didn't know about. Oops. We check a couple of feature flags in Redis, which is super fast, but it's still at the other end of the network cable, so it's another millisecond, more or less. And then we take all of this information and we render the view, which is quite large, so it takes a while. So that's what, 60, 70 milliseconds? This is reasonable for a web app in Rails. Like, this is on a good day. On a bad day, maybe more than that, like that. But who's counting, right? But this is basically my daily life as a Rails developer. This is where my intuition works. This is where, if I need to care about performance, I know where to look, and I know roughly how long things take, so I know where to focus. For other developers, though, this is very different. For example, if you're a game developer, you live and die in 16 millisecond buckets. If your game is going to run at 60 frames per second, you have 16 milliseconds per frame, non-negotiable. In those 16 milliseconds, you need to process your inputs, run your AI, your physics, collision detection, all of your game logic, some pretty particle systems, And then you need to take all of that and render a beautiful frame. And if you miss the 16-millisecond boat, you skip the frame, your game stutters a little bit, and then thousands of angry gamers will shout at you on Twitter. So it's a little terrifying for me how strict that is. And if you're a high-frequency trader, you're dying of laughter right now. Like 16 milliseconds is an unthinkable luxury. If you take just one entire millisecond, you're dead in the water. You can't even play this game. So the point I'm trying to make here is that what's fast and what's slow is really, really very relative to what you're doing. Some people are over here trying to get memory to be in big chunks all together, so the CPU caches are full and they shave some nanoseconds. Where I'm over here in milliseconds land trying to maybe not hit the database so much, right? Like the difference in scale is so large, it's insane. And so this is something important to keep in mind when talking about performance. Some things that, to me, as a Ruby developer, are amazingly fast. Somebody writing drivers inside the kernel, they can't even think of using them because of how slow they are for them. So try to keep that in mind when somebody says that something is fast or something is slow. That is literally meaningless without a context. But we don't think about it that way. We just go with this is fast and that is slow, and we internalize it as if it meant something. Now let's go back to our original question. Can we do this in a microsecond? Well, as I said, I'm used to these sorts of timings, right? For most of my work life, time exists in millisecond boxes. I cannot care about anything smaller than this. I have bigger fish to fry. So if you ask me, can we increment the hash in a microsecond is that much. In case you can't see that, it's that tiny red dot over there. So I have no idea. I live in milliseconds land, right? But we have two opposite opinions here. Surely at least we can figure out who was right. Well, the interesting thing is they both kind of were. Let's go measure and see what we find. The first problem you're going to have is that even measuring this isn't that straightforward. The normal way you would do this is with benchmark IPS. Basically, you give it a bunch of ways of doing the same thing. It will do them repeatedly and tell you how many iterations per second it got. And so you can tell which one is faster. The problem is, when the thing you're measuring is so tiny, the measuring mechanism itself is a significant portion of your runtime. The method still works when you're comparing different things because the overhead is more or less constant, so you will know which one is faster. But it's not going to help you answer the question, how long does it take to do X when X is this tiny? For example of what I mean, if I run this in my laptop, it gives me about 0.2 microseconds for incrementing a hash, which is great, but it's a lie. Because here's the thing. For each iteration, I need to run a block. And calling a block is really fast in Ruby. But compared to other things like incrementing a hash, it's still a significant chunk of how much time you're spending. If you do this, for example, and not use a block, now you're twice as fast, which is closer to the truth. And if you want to get even faster, you can remove the thing you're measuring, time the loop itself, so you can see how much time you're wasting, subtract the two, and we get something like this, which is, you can do this about 12 times in a microsecond, which is awesome. This is well within our budget. And that's it, right? I mean, we have our answer. First guy was correct. Ruby isn't that slow. You can totally do this in less than a microsecond. Except it's not that simple in our case. If we take a step back for a second, I'm talking about storing these numbers in hashes. But why? Why are we using hashes instead of integers? Well, the reason is when you have metrics, you don't want to have one number. You want to have more granularity than that. And so, for example, if you have payments, you don't want to just know how many payments you took. You want to know how many in each currency, right? So we have this concept of labels. We have these key value pairs that we call labels. And the way we do this internally is we store all of our numbers in hashes whose key is also a hash. And the reason this matters for our performance is basically the way hashes work. Like when you're getting something from a hash, you need to take your key, find which bucket it falls in, and then compare that key with all the other entries in that bucket until you find the one you want. When your key is a constant, you're comparing constants with constants. That's pretty fast. If your key is a hash, now that you found the bucket, you need to compare the hash with all the other hashes, which is much slower. Now, how slow depends on how big those hashes are. So, for example, if you have a metric with 3 labels, that's going to be 60 times slower, which is terrible for us. Now, how about a best-case scenario? Now, your metrics, in theory, most of them should have no labels. So if we try and use an empty hash as a key, that's a little under a microsecond, which is within budget, but we're getting quite close. And we're just incrementing a hash here. In real life, we need to validate those labels. We need to do some processing on them. And we're not even thread safe. We put a mutex around this to make it thread safe. And now we're at about a microsecond and a half, and we blew our target. So turns out, for our case, guy number 2 was right in the end. We cannot do this in a microsecond. But what I find interesting is not really which one was right. What I find interesting is that I just expected this to be an easy answer, right? I wanted one of these 2 guys to win. But there's no winners. Reality is more nuanced than that. And this is what I'm talking about when I'm saying that fast and slow are meaningless without a context. It's always more nuanced than that when you look into it. Bottom line, we cannot hit the target of incrementing our counters in less than a microsecond. We are already past it, and we're still in a single process. Now, we can optimize this code a little bit, but doing anything that's going to solve our multi-process problem in less than a microsecond is definitely not going to happen. But we decided to not throw the baby out with bathwater, right? Like, we can't hit our target, but we can try and follow the spirit of it, which is that instrumentation should be free. So we want to make this as fast as humanly possible. And because this is going to impact lots of projects for lots of companies, it's actually really worth investing a lot of time in making this as fast as we can, even if we can't hit that microsecond. Now, at this point, we have a basic baseline of times. We have a beautifully refactored code base that lets me experiment very quickly. So how do we solve this problem? Well, we experiment a lot. I mean, we have made it really cheap for ourselves to try different strategies. So we started trying pretty much everything we could think of. And I'd like to walk you through 4 of these experiments that we did. First up, let's make this real easy for ourselves. Ruby has this really unusual data structure called a p-store. Basically, it's a hash backed by a file on disk. Every time you write a value to this hash, the whole thing gets serialized and put into a file. Every time you read a value, the file gets read again, and you get that value. And there's a lock around that file. So you can actually do this from multiple processes at the same time, all competing for the same file. Everybody sees the latest data, and it's safe. Now, p-stores are used almost exactly like a hash. They have this idea of transactions, which basically allows you to set several values all at once without having to hit the disk for each one. And you basically just wrap your accesses in one of those, and you're done. And if you think about it, this is exactly what we need, right? I mean, we have this global hash shared by everyone. All processes see all of the data. We're done. The only extra requirement we had is it fast? And p-stores are not very fast. This is not going to work for us. But let's take one step back. What are we trying to do here? Well, basically, we're trying to have a chunk of memory that is shared between all the different processes, right? As a complete aside, one of the great things of working at my company is the amazing people I'm surrounded with. Now, granted, some of those people are trolls. But the trolls sometimes have good ideas. I mean, SQLite was probably not going to be the best way to do this, but he got me thinking, you know what's a great way of having a chunk of memory shared between processes? I mean, it's my favorite tool in the whole wide world. It's my good old friend Redis. Redis is basically a chunk of memory running in a process outside your app. All of your worker processes can read and write from it, and we all know it's super fast, right? So this sounds perfect. This sounds exactly like what we need. And actually, the Prometheus library for PHP uses Redis for exactly the same reason, so that was promising. So I wrote up a little store that used Redis as a backend. I was super excited because I knew this was going to be the solution. I fired on my benchmarks, and it was very disappointing. It's actually slower than marshalling an entire hash into disk every time. I was really sad when this happened, because I really thought I had it. But mainly, how? How can it be this slow? I mean, isn't Redis supposed to be super fast? Now, if you stop and think about it for a second, it kind of makes sense. Like, you talk to Redis over the network. Granted, it's localhost, but still, every time you talk to it, you need to make a packet, put it into a socket, send it over, Redis gets that, opens it up, parses your command, runs it, makes a response, packet, socket. There's a lot going on, right? Redis is really fast. For a database, it normally lives in its own server. You talk to it over the network. And those 60 microseconds we just saw, they're basically nothing compared to the network round trip. So it's really fast compared to other databases out in the network. But compared to something that's happening in your own machine, in your own process, like writing a tiny file, you never had a chance, really. So as I keep saying, fast and slow without context are meaningless. Now, at this point, I had no choice but to face the giant elephant in the room. The consensus from pretty much everyone on how to solve the multiprocess issue was that we should use memory maps for this. This is, for example, what the Python library does. But throughout all this project, I was trying really hard to avoid them. I really wanted to find a different answer. And if I'm being honest, the reason I was avoiding them is that I was basically afraid of them. Like, I didn't know what a memory map was. Before this project, I hadn't even heard of them. I didn't know how to use them. If you try to read up on them, it's not really clear what they are, what they're for, how you use them. The best thing you have is this, the kernel documents. And they're super useful in the description of the details of how each flag works. But if you don't know what this thing even is, this is not a very good primer. And I also saw some code examples that left me even more confused. Like, it looked like the way to get this shared chunk of memory was a file path in /tmp. I mean, that makes no sense. We were trying to not use files, right? Now, just another reason I was so confused is that maps are one of the most basic, fundamental building blocks of the kernel. This is not a thing to share memory between processes. This is a massive Swiss Army knife that you use to do all sorts of basic memory stuff. And the problem with the docs is that they have really good descriptions of each of the tools, but there's nothing that's going to give you the big picture. But it turns out there is one of these tools that is what we want. It's the shared memory mapped file. Basically, the way this works is a process opens a file, and it maps it to some place in memory. If you read that page in memory, you get the contents of the file. If you write to that page in memory, the file magically gets updated at some point later, whenever the kernel feels like it. But here comes the magic. If a second process maps the same file, saying that it wants to share it, both processes get assigned the same exact page in memory. So if one of these processes writes to that page in memory, the file eventually gets updated, but you don't care about that. What you care about is that the other process can now read that page in memory and immediately get the new data, which is magic. And the other thing you care about is that there's a file, but you're not really writing directly to it. You're writing to memory, which is as fast as writing to memory instead of being as slow as writing to files. And this is actually famously one of the fastest ways to do inter-process communication. So I can see why everyone was suggesting to use this. Now, there's one slight problem. mmap is a syscall. Do you all know how you call a syscall from Ruby? You don't. You do it from C. Now, granted, there's this thing which has the most hilarious line I've ever seen in official documentation. It's not particularly useful for this. And also, let's say you manage to actually call mmap with this. Now you have a chunk of raw memory that is yours and a row pointed to it. Now what? How are you going to read and write that from Ruby, right? So we're going to need some sort of wrapper to use this, and it has to be written in C or something similar. And I don't write C. I can barely read it. And I should certainly not be trusted to write some C code that's dealing with a syscall that I don't understand and is doing some magic memory voodoo that will run in production not only in my company, but in a bunch of other companies. This is not going to happen, right? But fortunately, we have this gem, which was originally made by a gentleman called Guy Decoux. But if you look at the repo these days, you're going to see a lot of this face. Now that is a face I trust. Like, this guy knows C, and he's normally found doing magic memory voodoo. This is definitely good news. Now, in case you don't recognize that, it's Aaron Patterson. He goes on the internet by Tenderlove. And he's one of the core Ruby maintainers. And you should watch his talk tomorrow, because it's going to be really interesting. But going back to our case, how do we mmap with this thing? Well, you basically make a file. You initialize it to a certain size, say 1 megabyte. And then you init this mmap thing. And now you have this m variable, which behaves sort of kind of like a byte array. So importantly, it is not a Ruby array. The mmap gem is doing a bunch of magic to map between the actual memory and things that look like Ruby. But it does behave like an array, so you can just pretend it is one. And if you have a bunch of bytes to write, you just set a range on the array, and that'll do it. Now, the tricky bit is turning the stuff you want to write into bytes. And to do that, you have these methods called pack and unpack, which will turn your Ruby stuff into bytes and then back into Ruby stuff again. Now, if you've never heard of pack and unpack, don't look them up. Just keep that innocence. It's really nice to not have to know about this. But in our case, we had to. And so we have a float, and we want to write it into this M thing. So we pack it into 8 bytes, which is how big a float is. And then we set those positions in the array, and we're done, which is amazing. And like for all the other stores, we need to figure out whether this is going to be fast enough, right? Now, to recap a little bit what we had so far, we had a hash with no synchronization, which ended up being a little under a microsecond. We have the same thing, but with a lock around it for multi-threaded applications, which is about a microsecond and a half. And we have the only reasonable solution so far for the multi-process problem, which is the p-store, which is a terrible 35 microseconds. And maps, which I really, really don't want to use, are actually quite fast, which I'm going to have to use these. And at the point, again, it looks like we're done, right? And I thought that too. But in addition to having a script that benchmarks these things and times them, I had another script to stress test them. Basically, this script would do terrible things to these stores, just to make sure they were safe. You would have a ridiculously large number of metrics with ridiculously large number of labels, and you'll be hitting it from many threads and many processes all at the same time competing for the same file, just hammering it to make sure it's solid. And as soon as I run that script on the mmap store, now, raise your hand if you've ever seen one of these in Ruby that was your fault. Right? I have 2 hands, and one is actually Tenderlove. That's the point. You're not supposed to see one of these. This is the famous segfault or segmentation fault. Or I think technically it's the scarier little sister, which is the sig bus. But it's basically the kernel telling you you've messed up real bad. And I don't know about you, but one of my favorite things about high-level languages is that I don't have to deal with this. I don't want to have to deal with this. I don't know how to deal with this. I don't know where to start. This is precisely why I don't do C, so I don't have to think about these things. But I asked around, and apparently this looks like garbage collector related. Like something was freed, and then it got cleaned up, and then I was still using it. But the problem is, what do I do with that? As far as I knew, I wasn't freeing or not freeing anything. I was just using this gem that gives you this thing that looks like an array, and now I have a segfault in my face. And this is precisely why I was trying to avoid the memory maps, right? I was worried about this exact thing happening, and now it happened. And given that this was a gem written by Tenderlove, and it was being used by me, this was most likely not a bug in the gem. I was almost certainly using it wrong. But this is a fairly obscure gem. There's not that many people trying to do M-maps in Ruby. There's nothing about it in Stack Overflow. I haven't found anyone actually using it. So it's kind of hard to figure out what I'm doing wrong. Now, experimenting randomly, I basically figured out that this was related to some code that I have to resize the M-maps if that initial 1 megabyte wasn't enough. So if that code ran afterwards, I would get the segfault, but not immediately, a while later, which kind of points to the garbage collector, right? So that's great. We have no idea why this happens, but at least I can reproduce it reliably. And like always with these problems, if you want to solve it, you basically try random stuff until something sticks. Now, it took a while, because I had no idea what I was doing, but I actually made the segfault stop. It was this elaborate dance of flashing the file, closing the file, reopening it just to resize it, then closing it again, then opening it again, and mapping it again, and the segfault stop. Now, if you have a problem, you don't understand the problem. You try random stuff until the problem doesn't happen anymore, but you don't know why it was happening or why it stopped. How confident are you that that's not going to happen again in production in some random server, in some random company's mission-critical app, right? I really wasn't. I did not like this one bit. And in addition to that, there are other downsides of using this mmap gem, because it's a C extension dependency. These are the ones that get compiled when you install the gem. For example, they don't work on JRuby, at least not directly, and we do want to support JRuby. And they're also tricky. Like most of you probably had trouble installing Nokogiri at some point in your life, right? Like C extensions can be a pain. But most importantly, it may be kind of segfaulted, which is like not ideal. So it was fast, but we wanted to keep looking. And of all the interesting things we found in this project, this last experiment was by far the most surprising. With the memory maps, we were working with a file, doing the kind of things that you do with a file. We were just doing it in memory, which is faster than normal files. But what happens if we ditch the M-maps and we just do this to a file? From the code perspective, pretty much the only difference is instead of setting a range in a thing that's pretending to be an array, you just call a couple of the file functions to jump around and to write. And the interesting bit is you're doing the minimum amount possible. You're not Marshall dumping an entire hash into a file. You're just doing one jump and then writing 8 bytes. It's pretty efficient. And that was pretty much the whole change. I mean, we have no emmaps, we have no C, we have no segfaults. There's nothing fancy. It's just plain old boring Ruby writing bytes to plain old boring files on slow hard drives. But as usual with these solutions, we need it to be fast. And this, I mean, how slow was this going to be, right? And before I tell you, I want you to visualize how slow disks are. I mean, we use Redis and Memcached famously because they're in RAM and not on disk, right? We use RAM drives and tempfs so we can work with something that looks like files but not have to use the disk because they're slow. We give our databases gargantuan amounts of RAM so you can keep everything there and not have to touch the disks because they're so slow. So how slow was this solution based on disks? Well, if you remember, the emmaps were about 6 microseconds. Files on actual hard drives? 9? I mean, considering how slow I expected this to be, this completely blew my mind. If you compare this to memory maps, we have no external dependencies, no risky C code, definitely no segfaults. It's compatible with all editions of Ruby like JRuby. It's 100% understandable by any Ruby developer. And most importantly, there's nothing in that code that keeps me up at night. All of this for just 3 extra microseconds? This was a complete no-brainer. And that's pretty much it. I mean, we ended up picking disks as our end solution because it was fast enough. And we think that the trade-off is more than worth it for the peace of mind that this solution brings us. And this is where this talk should end. I mean, we solved the problem with a fast, elegant solution. We got our code merged. We're now maintainers of the gem, which is pretty nice. And now people can use Prometheus and Ruby, right? Happy times. But this is a funny result, isn't it? I mean, memory is supposed to be orders of magnitude faster than disk, thousands of times faster. And I'm telling you it's like, what, 30% faster? Like, what's going on here? Well, as I've been saying, it's always more nuanced than that. Now, first of all, writing to memory should take nanoseconds, not microseconds. And what's happening there is that the thing that I have is not an actual array. The mmap gem is actually doing a bunch of magic to map from one thing to the other, and it has to synchronize between processes, and it takes a while. But more importantly, if you are at all used to performance numbers involving hard drives, you're probably looking at this number with a lot of suspicion right now. And you'll be right. Because what's happening here is that I'm basically cheating. I mean, it's a fair cheat. It works for my use case, but I'm still cheating. You see, actually putting stuff on a disk is slow, but this is not what happens when your app writes to disk, at least not on a modern operating system. When you tell the OS that you want to write to disk, the OS takes note of that and goes like, yeah, all right, I'll get around to that at some point. But it doesn't actually write to disk right there. Like, it'll do it later, at its leisure, whenever it's convenient. And normally, this is a problem for you. If you're a database and somebody sends you data, would you trust this dude to actually do it later? I mean, of course not, because when somebody trips on your power cable and the OS hadn't finished chilling, you lost the data, which in the database world is generally known as no good. So you have to fsync, which is literally telling, like, hey, those things I told you to do them now, I'll wait. And that is slow, because you're actually writing to the disk. If you're a database, sadly, you're going to have to pay that price, because you really care about that data that you're writing. But I'm just storing metrics for this particular run of my app. If my app gets killed, I mean, Prometheus has the number so far. Next run of my app, I'm starting fresh from 0. I don't care if that data stays. I only care about this data while my app is running so that the processes can see each other's numbers. But once I'm dead, whatever. I'm starting over anyway, which means I don't have to wait for the data to actually get committed to disk. And now it's not slow anymore, because when I'm writing to disk, I'm really just writing to that bit of memory where the OS makes a list of the things that it's going to write to disk, which is cheating. But it doesn't mean you can't do it. It just means I have this very unusual use case where I can get away with pretending to use disks without actually having to pay the price for doing it. So is memory fast? Are disks slow? Well, as I've been saying, Depends on the context. So we've covered a lot of weirdly specific ground all over the place right now. But what is the point of me being here? What am I trying to say? There's this age-old saying when it comes to performance optimization. You've probably heard it. Measure before you optimize, because the thing that you think is slow is probably not the thing that is actually slow. And we all know this, and when I was trying to figure out where my code was spending time, I definitely measured, and I definitely found surprises. There were definitely cases where my expectations were wrong. You know, like the expert said, they were right. But what I found in this project is that that's not enough. Now, as I said at the beginning, this is not a talk about memory or disk or microseconds, files, or hashes. This is a talk about assumptions. When we decided that the solution to a performance problem, where we needed to do something really fast, was to put stuff on a disk, I was shocked. I was completely stunned. And the reason I was shocked is that, like everybody else, I knew that disks are really slow. In fact, if you had told me before this project that Marshall dumping an entire hash into a file would be twice as fast as hitting a localhost Redis server, I would have laughed so hard I would have needed medical attention. Because I just knew that's just not true, right? But here's the problem with these things we all know. They're normally very simple. They're very memorable. They have to be if they're going to spread and stay in our heads. Ruby is slow. Ruby can't possibly be that slow. Surely you can read and write a hash in under a microsecond, right? Can you? Yeah. Can we? Well, no. We're doing something weird with them for good reasons, and it's slow. Memory is fast. Disk is slow. Redis is fast because it doesn't use disk. Now, is it fast? Yeah. For a database, it's really fast. Is it faster than disk? Well, depends. The problem is that there's a lot of nuance around these simple truths, and it gets lost in the process. If you look at them up close, these questions aren't simple. They don't have straightforward, simple answers. And everyone that believes them hasn't actually checked them in the context of their own problem. I mean, of course not. We already know the truth. But the reason that's a problem is that having these things we all know is going to make you blind to potential solutions that you could otherwise see if you didn't have this knowledge. Like, take this project, for example. It's not like at the beginning we all got together and we discussed it and we explicitly discarded disks because we thought they would be too slow. We didn't even consider it, didn't even cross our minds, because implicitly we all knew that it wouldn't work. Now, I landed on this by pure luck. I happened to notice that the memory maps were opening a file anyway, and it'd be easy to make them do the same thing without the memory maps, and so I tried it. But I didn't try it because I thought it would be an actual potential solution. I tried it out of pure curiosity. I knew it wasn't going to work. I just wanted to see how much ridiculously slower it would be. And if I hadn't, to this day, I wouldn't sleep well, wondering when that segfault was going to hit someone in production. So what I'm trying to say is, when you're trying to solve a problem and figuring out how to approach it, try to be aware of that filter in the back of your mind that's discarding options because you know they wouldn't work. Try and pause and look at those options. Like, why do you think they wouldn't work? Are you sure that's actually true? Can you do a little experiment? Can you measure things? Because there may just be a really straightforward solution that you're missing because it wouldn't work. Sometimes it does. Thank you.